Just wanted to really start by acknowledging, though, the contributions from the Forest Growers Levy Trust and MB to this program. If it wasn't for their support, obviously we wouldn't be here and the industry wouldn't have this particular program. And just also want to echo Russell's comments around our appreciation for the technical committee, who basically given up a lot of their personal time to provide input and guidance to the program, and particularly help us kind of bridge what is often referred to that valley of death between developing research and actually having it implemented. And so by having people who are working in the industry around the table discussing the research and looking at the implementation has been very, very helpful. As Russell said, the very ambitious, stretchy goal of the program is really to have a quantum lift in productivity of radiata pine, and we really talked about the idea of doubling it. And there is no silver bullet solution for doing this. If you're going to double productivity or create a real step change in productivity, it's going to come by doing a number of things throughout the forest growing cycle and doing them well. And so that was really the concept of the Gcff program, was to really take an integrated approach. Rather than just focus on one particular area, we wanted to focus right through the forest growing cycle. And so that's what we have there shown on the right. If you think about our current forests, the wood that we're going to get for the next 20 years or so, it's already in the ground growing. So what opportunities have you got to influence those stands? You can do mid-rotation interventions. You can make sure that we get the full benefit of those existing forests at the time of harvest. And then what we want to do is, having harvested those forests, is look at the future forests. How do we increase the productivity and consistency of those forests through deploying the right genetics that we've just heard in the previous session, through getting the management right, and also the nutrition that we heard a little bit about. And so that's really been the focus of the program. And at the core of that has been this drive to get better information. Actually, one of the things that Mike Reardon, phrase that he often used, was you can't manage what you can't measure. And so in the centre of that core of that diagram is this concept of the phenotyping platform, which I'll leave to Mike Watt to describe a lot more about, but fundamentally it's about using the latest advances in technologies to really understand how the combination of genetics and environment gives you the particular phenotype, or what you actually observe with your eyes. Because it is a very complicated program, we talked for quite some time how we were actually going to structure this presentation, and we actually thought, given that for the audience, we actually need to present it in terms of how you would basically make decisions about how you manage forests. So if you think about it, looking at the top of that diagram, all the decisions that go into growing a forest, where to plant, what to plant, how to raise that material, how to manage it, how to monitor it, and then how to realise the value at the end and actually protect the land after you've harvested. That's how we're going to structure the presentation. So this wheel will appear a number of times in the presentation, just to kind of check in with where you're at. It was good to see that the video worked, because we've got a couple of video interludes, so it's not death by PowerPoint. But really what we're focusing on is, particularly in here, is this concept of precision forest management. And all the work that we're doing in the program, we're testing it through what we've called the accelerator trials. So this idea of how much can we push the boundaries of radiata pine, how much can we accelerate things. So the best research that we're doing, we take that, we put it in the accelerator trials, and they will generate information, but they will also be one of the legacies of this program. So without further ado, I'll hand over to Loretta, who's going to start off.
Thanks, John. Morning. Yeah, so where to plant? The Growing Confidence program, we've had multiple focuses, and this one, where to plant, we have improved forest value from putting forests in the right place and understanding what to plan for. So there is a wide range of site quality in New Zealand where forests are planted. Each give different benefits and challenges for sustainable long-term productivity. So where should we plant to maximise those benefits? This figure shows an example of possible future forest locations under different scenarios targeted at erosion control. It demonstrates where there could be a large amount of land that could benefit from planting forests. Understanding the benefits from these new plantings can be done using a science model called the Forest Investment Framework. This is a model that represents forests' full value in decision making. So forestry provides multiple values to the economy, environment and society, and many of these benefits do remain poorly understood and are often ignored in policy. The Forest Investment Framework, also known as FIF, is a scientific valuation tool to robustly quantify forests' multiple values to enable their representation in policy. FIF combines biophysical, economic and environmental data. It allows us to understand the viability of exotic and native tree species, and it has spatially explicit values of non-timber benefits, for example carbon storage and avoided erosion. Through the Growing Confidence program, FIF has been further improved to include a biodiversity conservation economic function and developing new spatial economic functions for nutrient mitigation, stormwater mitigation, water filtration and recreation. FIF has been widely used in New Zealand. It's been applied to more than 18 different case studies. These include government agencies, iwi groups, scientists and forest companies. We've also been recently contacted with requests to apply FIF to other areas, for example the Hawke's Bay, the Rotorua catchment and other planted forest estates. And FIF will more than likely be involved in the One Billion Tree program. So we're quite excited by this particular valuation tool. FIF can also be used at the national level, as demonstrated in this example of projected returns from radiata pine, basically showing what forests are profitable and what are not. So there's quite a lot of benefit in the model. In this large program, we've also had a focus on understanding what a site's potential productivity could be, and therefore where sites' productivity gains can be made. We have developed a national productivity gap map, which determines where interventions will provide the greatest payoffs. The green and blue areas in the map show the sites that have the largest gap. Overall, New Zealand's planted forests are about 18% below their potential maximum. Therefore, the national potential to improve planted forest productivity is there. We have also done much work on predicting productivity from understanding of site nutrients. This has been done through the model called the Nutrient Balance Model, also known as NUBAM. NUBAM can be used to understand site nutrition and the implications for productivity before trees are planted. It calculates both nitrogen and phosphorus demand in the growing stand in any given year, over a rotation and over multiple rotations. It can also predict fertiliser need to meet a chosen target productivity. All of this has been made possible as the site is now capable of being site-specific, predicting for macronutrient requirements. It is linked to the Forest Carbon Predictor model, which you may know about, and we're also looking at linking it to Overseer. So this slide shows an example of how NUBAM can show a growing forest's nitrogen surplus and deficits on an annual basis. First up, you'll see that there's a surplus of nitrogen as the plants are young and unable to use all the available nutrients on site. Then, as the forest grows, there is a peak nitrogen demand about 4 to 7 years old, where the canopy of that forest is building. If the site is low in nutrients, the peak demand may not be met, resulting in a deficit and a loss in productivity. If a thinning event occurs, you also get a second peak there in demand. As the forest grows, so too does the forest floor, which will eventually start cycling and supplying nutrients to that forest at later stages in the rotation. So to end this little section on where to plant, the Growing Confidence in Forestry's future program has enabled both the forest investment framework and the nutrient balance model to be further developed. It has generated a national productivity gap map. All give information to support decision making on where planted forests, on putting planted forests in the right place and understanding what to plan for. That brings us to the next one, which is Mike.
Thanks, Loretta. For those of you who don't know me, my name's Mike Watt, and I've worked at Scion for 15 years as a scientist and senior scientist and research leader. Currently lead the geomatics team, which is a fusion of GIS and remote sensing research. And I'm going to present to you on what to plant, and by what to plant I mean, excuse me, what sort of genotype to plant out. We're talking about radiata here. I'd like to start off by acknowledging the team associated with this. It's been a really interesting mix of genetics and remote sensing. And if I could just single out a few people amongst the team, I'd just like to particularly acknowledge Dave Pont, Heidi Dungay, Jonathan Dash, and Maxine Bonbrum, who have been associated with the individual tree phenotyping and the area-based phenotyping. So in terms of the overall value chain, where does this fit in? So advances in phenotype will enhance forest productivity for allowing better matching of genotype to site, which kind of addresses the questions raised by Ewan and Bruce in the last session. So we'll get to that later on. So if we look at this slide here, phenotype is what you see, basically, and it can be measured in terms of tree dimensions such as height, diameter, crown width, and this phenotype is the product of genotype and environment and the interaction between genotype and environment. So if we really want to work out the productivity of different genotypes, we need to disentangle these things a little bit, which is really the sort of basis for the phenotyping platform, this new concept we've developed. And I hope to be able to demonstrate that this will allow us to better match seed lot to site based on past and current performance. So the phenotyping methodology that we've developed, there are 2 levels of phenotyping. There's the area-based phenotyping, which you're sort of looking at in the top there, up the top there, area-based phenotyping. And this is at a 25 by 25 metre resolution. So this will include a number of trees at that spatial resolution, and that also happens to be the spatial resolution of LiDAR. So that's a reason why that was selected. And then we have tree-based phenotyping, which is basically, as the name suggests, working at the tree level. And we have started applying that to stands, and eventually we hope to be able to apply it to the entire forest estate. But as you can imagine, it's a lot more computationally intensive. So I don't really want to scare you with this diagram, but if you do have time to go through it, it does actually have everything in there. But if I could just point out a few things around how the area-based phenotyping works, that would be great. So basically it takes the data from the LiDAR survey, management records, climatic models, takes information about the seed lots, the management. It takes the data on phenotype, which in this case is 300 index and site index. I think John's explained these previously. Site index is the mean top height at age 20, and 300 index is the volume analogue of site index. It's the MAI, mean annual increment, at age 30 for a stand growing under 300 stems per hectare. So we've chosen these as a phenotype for this this approach. Then it puts all these together into a modelling approach, and site index, 300 index are predicted as a function of climate, the actual seed lot management, and any sort of terrain attributes, soil data that we have. And then from this modelling approach, we actually partition out these effects. So we use quite a sophisticated modelling approach for this, and the data and the model is applied across Kaingaroa Forest. So it's a pretty ambitious sort of project to apply it right across Kaingaroa Forest, but also fairly useful. So as I mentioned, the seed lot information provides us with a starting point. Climatic data is then integrated to identify the key site properties, and this allows us to assess the genetic effects independent of the site effects. So as you can see, in Kaingaroa Forest we have a lot of different seed lots, and they're pretty well dispersed throughout the resource. And of course this becomes complex because when you overlay climate, you've got these seed lots growing under a range of different climates. You're just looking at one particular climatic variable here, but there are many climatic variables used in the analysis, and so you need to somehow include all this information in the model as well. So here are some early results. Basically, we found using gradient boosting machines, which is a very sophisticated machine learning method, which has been cleaning up a few competitions around the world. We were able to account for 70% of the variance in 300 index. And the good news for you guys is that seed lot was the top variable influencing the productivity. And of course that's something you can change. You can't change spring temperature and summer temperature. Well, I guess as a whole we all are around the world, but you guys probably have limited ability to change it yourselves. So that's really great. You can start to work out where to place these particular genotypes. So, and this is really where the rubber meets the road. So we've used it successfully to predict 300 index values for a clone that I won't identify here for privacy reasons, and I won't identify the scale as well, but this is basically 300 index going from low values as shown in orange through to high values as shown in red. And so the first point is that the predictions match very well with the observations. It's always good when you're developing a model to see that. Second point I'd like to make is that we're now looking at the G by E effect for this particular clone, and this is a way of presenting it. So it sort of addresses the questions that Ewan and Bruce raised earlier about how do we actually predict this. Even though we don't understand the physiological drivers from this particular model, we do have a means of actually displaying this. And you can imagine if you had a number of different clones, you could quite easily compare these and work out where to best place each clone. So I'd like to move on to the tree-based phenotyping. This is work that's been spearheaded by Dave Pont. And once again, LiDAR data has been used for this to carry out tree detection and crown delineation, as shown in the top image. Dave has identified crown metrics that accurately estimate tree height and volume, and LiDAR is very useful for these two metrics, and is currently in the process of detecting and characterising every tree in an operational stand, as shown here, of around 30 to 40 hectares. So this is a massive task, 10,000 trees, and Dave has developed a process for doing this, which is really, really amazing that this has been done. And once again, with the area-based phenotyping, Dave has had to develop a model that partitions the genetic effect from the microsite and the competition effects to achieve this, because it's not just a matter of going through and finding the biggest trees within the stand. We can already do that from LiDAR, but it's a matter of finding the trees that are growing the best given their set of conditions. They might not necessarily be the biggest trees, they could be just medium trees growing under poor conditions, might actually be the best genetics in that particular stand. So there's been a lot of work around this. And so the benefits of tree-based phenotyping is that you can quantify the genetic by environmental by silvicultural interaction to determine tree growth, identify superior tree performance And I think we use the snip chip technology that Heidi referred to previously to do this. And of course, as Heidi previously described, this allows us to shorten the breeding cycles and also allows us to optimise the matching of breeds to sites. We're really moving towards, with this sort of technology, we're really moving towards a precision forestry paradigm. There's been a lot of discussion about this in the past, but I think this is a very good demonstration of that concept. And ultimately, this method will support higher productivity, higher returns from stands. Of course, moving forward, this is really great. I'm really proud to be associated with this work. It's great work. But I think there are some significant gains we can make on this. And of course, there are limitations to what you can actually see from above, because a lot of the key variables that drive value are actually not that well seen from above, such as form, branching, and stem size. So really we need to move towards exploring LiDAR from below in the form of terrestrial laser scanning. And we've done quite a bit of research around looking at the utility of this device here called the Z1. Basically, you just walk around the stand and you flap it a bit, like that. And if you walk around enough different places, you can put together a coherent point cloud of the stand using this device. And we've actually shown that has it's actually more accurate than the higher resolution devices which sit on tripods and you have to shift around. Because you're moving around, you actually get a lot more different viewpoints, and that actually turns out to be a more useful device for that. And so once you've got this sort of data, you can do all kinds of interesting things. Dave has actually created what we call hyper LiDAR by merging the point cloud below with the point cloud above. And of course, these both have their own strengths. And so you can get these sort of outputs such as this, which is really exciting to see this sort of data coming through. So we'd like to work a lot more on this in the future.
I think we'll take a walk in here and look for these two red trees, which Dave's identified as potentially being large trees for the area. So first tree of interest is 32 metres away, 20 metres to go. It's a big tree, it's a straight tree. For where it is, it's probably been advantaged a little bit. It's on a north face, so nice environment. A few of its neighbours are missing, so it's had a bit more space to grow in. We'll put this into the next stage. So the next stage is mark it up, get increment core to work out the density of it. We'll bring an acoustic tool to get an estimate of the stiffness at breast height. And then lastly, because this stand, we know the genetic origins of it, because it's seed orchard based, we will take a bark window out and take a sample of cambium back to the lab, and the girls in the lab should be able to, with DNA fingerprinting, tell us who mum and dad are for this tree.
Well, good morning everyone. So I'm just going to move on to the next stage of the presentation. My name's Simeon Smale and I work at Scion. I've been involved with Scion since about 2000, just as part of my postgraduate studies at University of Canterbury. And in 2008 I got a full-time position, and I've been happily working there ever since. So in this presentation we're just going to start off with some of the work we've been doing in the nursery, which is the next sort of phase in the circle, how you can raise that stock once you've identified what it is that you want to be growing. Again, as with all of this Gcff work, there's a great big team involved, so there are a lot of people to thank, but also particularly like to single out some of the support we've had from our industry partners. So Mark Ryan at Arbogen has been an early supporter of all of this work, but a lot of it also goes back to Nigel Heron and also Warwick Brown at Tenai Nursery as well. So we've had really great support to allow us to take some of our work and put it into an operational framework quite quickly. So going back to the diagram, I suppose where we're really looking to add value out of this work is to support the production of better quality stock, and also to provide more options for the nursery sector to actually remain competitive and viable, find ways for them to be more efficient whilst producing that better quality stock. So one of the key issues we identified early is the use of fungicides in nurseries. Radiata pine nurseries are monocultures. They've often been in the same location year after year. It's a perfect environment for disease to come through. So for the longest time, fungicides have been an essential part of nursery management. But we became quite interested in looking at what are the impacts of those fungicides on the good guys, the beneficial fungi that are important to forest productivity, which are known as mycorrhiza. So we were keen to explore reductions in fungicide use with the idea that could we actually support better mycorrhiza while still maintaining plant health? And we found that it was actually quite feasible to do this work. So we've gotten from a number of trials consistent evidence now that we can reduce fungicide use and maintain crop health. And not only are we able to use less fungicide, we're actually getting better quality stock out of the end. So we're seeing better mycorrhiza on them in terms of not all mycorrhiza are created equal. Some are far better, it seems, for the seedlings. So we're able to shift towards a better community. And that's allowing the seedling to pull greater nutrients into itself by the time it's left the nursery gate. Now, to be very clear, I am not advocating no fungicide in nurseries. You still have those core problems of it being a monoculture. So you do need to have disease protection, but there are clear options for fungicide reductions. And just a little bit of evidence to support some of these claims. We have an operational example here at Tokoroa Arbogen. So on this side here, what we did is in our trial settings, we were able to have little patches and plots of different fungicide treatments. But here we just went to a simple brute force solution. Every second bed gets fungicide and the alternate bed did not. It's just a simple operational way to reduce fungicide use by 50%. So here we had fungicide application and no fungicide, and that cycle was repeated throughout this whole bay. And the results we had were pretty stark. Basically, a standard fungicide treatment where every single bed had the standard fungicide treatment, had a lower level of growth than those that were part of our trial, where they were the received treatment, so they got fungicide, but the neighbouring beds did not, or the best performing seedlings came from the beds that didn't get any fungicide at all, but their neighbours got fungicide. And across the board, we saw no impact on disease rates at all from this treatment. And this was over about 2.5 kilometres of seedbed sited in the most disease-prone part of this particular nursery. Another option we've been exploring is doing better with fertiliser use in nurseries as well. Again, many nurseries have been active in the same location for decades, and there are problems with soil fertility that are ongoing. And so therefore fertiliser use has become an important part of nursery management. But we started to think that the fertiliser use was probably excessive, and at the same time we were seeing nurseries having increasing problems with licence to operate issues around their nutrient use, around consent from regional councils. So we explored not only reductions in fertiliser use, but also the application of new and different products that could provide the same nutrition to the seedling, but in a much more efficient way. And again, the results from several years of trials show that, yes, we can do this. We can reduce the nitrogen loading without any ill effects. And in fact, we've found that by using a novel nitrogen source, which is Bioret, that we're actually able to add a fraction the amount of nitrogen and still get the same nitrogen into the seedlings leaving the nursery gate. And we're seeing better growth as well. Overall, there are many opportunities for efficiency gains in the nursery that are not just improving the productivity and improving the seedling quality, they're also addressing some of the licence to operate issues as well. So again, some of the data around this. So this is from a different trial, again at Tokoroa Arbogen, but again we had our standard, aim at this side of the room now, we have our standard nursery treatment here, so that had basically a full dose of nitrogen delivered in the form of urea, and then we're comparing that to quarter the amount of nitrogen added as our Bioret supplement. So again, we have a growth gain, and then half the amount of nitrogen added as a novel nitrogen supplement, Bioret. And that was quite positive, so we decided to extend it to a much bigger trial, this time over about 7 kilometres of seedbed. And we had our treatment in this case was a 60% reduction in nitrogen. So again, we were comparing 100% nitrogen in the form of urea or other conventional fertilisers versus 40% of that dose in the form of Bioret. And again, we found no loss in seedling growth. The uptake efficiency was greatly enhanced. Basically, the seedlings had the exact same amount of nitrogen in them leaving the nursery gate, despite the fact we'd added a lot less. And we actually had stimulated the uptake of other nutrients as well. So they had more boron in them. They also had more cations in them as well. We didn't add any of those, just the presence of the biorette stimulated the uptake of those other elements. However, there's a big so what question, that it's really nice to have better seedlings leaving the nursery gate, but what does that actually mean for performance in the forest? So what we've done is we've done some work tracking that, and from our oldest trial, which is now about 8 years old, but it's just gone through some thinning, so we're just about to do some more measurements on it, we found that after 6 years, seedlings that had been exposed to less fungicide back in the nursery, back in about 2010, had a significant gain in basal area, just purely as a legacy effect of what happened to them in the nursery. No other treatments were applied, we just took them out of the nursery, planted them at a site in Kangaroa and just saw what happened next. And after about 2 years, we saw gains starting to appear from that reduced fungicide use back in the nursery. And we see that as being driven by better early establishment, which allowed greater growth and certainly better survival. And that probably came from the changes to the mycorrhizal community present on those seedlings when they left the nursery gate. So that fungicide, the reduction in fungicide was enabling better mycorrhiza, and you had a payoff in the forest. Again, there's a bit of another caveat to this, as this is only one site. So in order to see if these results were general in terms of the nursery legacy effects, we had our one site back in 2010, and under the Gcff program, we've been able to expand that out to a further 54 sites around the country. Again, these are a little bit younger, so we don't have the longer term results, but we are seeing them to generally be on the same trend, where there are positive legacy effects from better management in the nursery. Gains are continuing to come through from reduced fungicide use, but we're starting to see positive field gains from the biorette use as well. And the network, the size of this network, indicates we're also in the position to start developing nursery recipes that suit a particular part of New Zealand, so you can basically prepare your seedling more effectively for where it's going rather than just to a generic recipe. However, there are some negatives that we've picked up from our engagement with the nursery sector under the Gcff program. Labour issues are clearly a big issue for the nursery. Maintaining a workforce for what is not necessarily a pleasant job during winter is a big problem, so they see automation is going to be a necessary thing to maintain the viability of the nursery sector. And with that, you also see new opportunities around surveillance to manage disease, to help that, and to manage nutrient issues, to look at stock, to inform that automation to allow it to be as effective as possible. Increasing licence to operate pressure, which I talked about in relation to nutrients, is also a problem. So overall, there are a number of nursery managers that are relatively pessimistic around the ability to stay viable with the conventional nursery practice. So we are seeing some opportunities to change nursery practice, but I think it's going to be quite important to employ those as soon as we can, not just for the productivity gains, but to just enhance the sector as a whole. Now we just have a couple of videos.
These fungi are really important to the performance of radiata pine. They help them get nutrients, they help them get water, so they're really important to their early establishment and their survival. So working in a nursery, we basically increased or decreased levels of fertiliser and fungicide addition by 25% in all possible combinations. And leaving the nursery gate, we got some really interesting results showing that the seedlings that had reduced fungicide exposure had much better mycorrhiza on them. Not all mycorrhiza are created equal. Some species were clearly doing more for the seedlings than others. So that was all well and good, but we really wanted to see, well, what actually happens when you plant them out in the forest? How significant is the response of the ectomycorrhizal communities to reductions in fungicide and reductions in fertiliser? So in 2010, we planted these seedlings out, and then we've been monitoring them pretty much ever since, and we've got some pretty nice results which basically show the seedlings that were exposed to less fungicide in the nursery have a higher survival rate, and they've also been growing faster as well. So here we are now, a number of years later, and the basal area of the seedlings that had less fungicide way back, 8 years ago, back in the nursery, it's 8% bigger now.
We've done some trials around fertiliser use. It actually coincides with some research that Sion and Simeon Smale has been doing, and that's demonstrated that reducing fungicides and fertilisers significantly actually improve mycorrhizal activity in the trees. So they're the two things that deplete mycorrhizal activity. And when they go out into the forest, those trees survive and perform better than trees in a standard production system. We've actually just taken 40% out of our total crop this year, 40% of our fertiliser application, and the trees are looking really good. We're satisfied that that might be a new baseline until we get further information.
Thanks for that, Simeon. So I'd like to move on to the next section, how to monitor and manage the resource, and both myself and Simeon will be presenting this. And once again, I'd like to express our thanks for the core team who've done this work. Very excellent research has gone on here. So in terms of how this fits into the value chain, basically the objective of it is to make a step change in the ability to monitor almost all aspects of the forest, and I believe we've achieved that, and develop many new options for efficient interventions. And I think there's been a lot of progress made in this regard as well. So when I look back to research we undertook 5 years ago, we're really around looking at predicting stand metrics, such as mean top height, diameter breast height, and the rest of the usual suite of metrics for Douglas fir from LiDAR data. Seems like a long time ago now, but that was really the stage we're at that point, and we were able to successfully demonstrate that. Using LiDAR, we could predict these metrics, so we can move to spatialising inventories using this data set from Blakely Pacific, from the southern South Island. But one of the key points that came out at this point was that we were able to actually thin these point clouds down from the collection intensity of around 10 pulses a square metre down to 1 pulse a square metre. And we found very little change in the precision of these relationships. Basically, these graphs just look the same when you went down to 1 pulse a square metre. And of course, LiDAR cost scales with the pulse density, so it was a very useful finding for us at that stage. And also, we knew that Douglas fir stands were a lot denser than radiata stands, so if it worked in Douglas fir, it's likely to work in radiata, and it's held up pretty much since then, that finding. Other early research which we undertook was the development of a national model for predicting height and volume from LiDAR data using an extensive data set, as you can see on the map on the left. We were able to develop pretty strong models with mean top height and total stem volume. And why is this important? Well, as we do move towards regional LiDAR acquisitions, or if you do have a massive LiDAR acquisition but you don't have any plot data, this could actually provide you with a useful starting point for predicting mean top height and volume. We also undertook research that developed methods to model site productivity in terms of site index and 300 index, and key stand metrics from LiDAR, satellite imagery, and environmental data. So basically the key finding in terms of site productivity metrics was that LiDAR is the premier form of data for predicting these metrics, such as 300 index and site index. Up to that point, we'd been using environmental services right across the country, and we found a significant gain through using LiDAR to predict these metrics. So that's very useful auxiliary benefit of having LiDAR data, is that you can predict these across your estate. And as I showed in the phenotyping platform presentation just previously, that could obviously have a lot of benefits in itself. We undertook research just looking at how different forms of remotely sensed data can be used to predict the standard stand metrics, such as height, base area, total stem volume, and stand density. And if you look at the slide here, you can see a very definite threshold once you have LiDAR data. If you add other forms of data to this, such as rapid eye, which is satellite imagery, environmental surfaces, you get very little change in the precision, or R squared, over here. And once again, if you don't have LiDAR, you're really at a lower precision. But I'd like to add the caveat here that this is really just imagery from satellite. It's not actually the photogrammetric point cloud, which I'll talk about a bit later. This is actually a very efficient way of predicting inventory metrics as well, but certainly just in terms of the imagery, LiDAR provides you with a better precision. We've used remotely sensed data as inputs into the forest scales model to spatially predict the risk of wind damage. So basically, LiDAR data has been used to spatially characterise stand structure and used alongside a number of other input variables to show the current probability of wind damage, and I think this is a really exciting result because we're now able to spatially predict areas, you know, where the actual most prone areas are, and I think that's a really great move forward to be able to do that. Another very interesting piece of research is the comparison of stereo satellite imagery and LiDAR for inventory purposes. So by stereo satellite imagery, I mean the photogrammetric point cloud from overlapping satellite imagery. You can be used to create a point cloud which is very similar to that of LiDAR, but the key difference is it's a lot cheaper. And so if you have a look at the image up here, what you're looking at here is a canopy height model from LiDAR versus a canopy height model from satellite. And the interesting point to this is these green areas predicted by the LiDAR, which are the ground, are not so well picked up by the satellite CHM. This is Geraldine Forest, by the way. But it doesn't really matter because most of the predictive metrics for the key stand metrics that we're interested in are actually in the top half of the canopy, so that's not such a critical point. So the net result from that is when you compare the error, and shown on this table, root mean square error, between the LiDAR and the satellite imagery, it's very little difference. So this is a really important result, and I think we should push further on this in terms of looking at how can we use photogrammetric point clouds from a fixed wing aircraft, which are, you know, this data is really widely available to actually predict the standard metrics as well. We've demonstrated that useful models of leaf area index can be developed from an extensive LiDAR dataset collected across Kaingaroa Forest. From my understanding, this is the best dataset of its kind in the world, and model predictions were made with a reasonable level of precision. Why does this matter, you might be thinking? Well, basically, if we can predict leaf area index and we can get some estimate of the foliage chemistry from hyperspectral data, which will be free within a couple of years from satellite, we can actually move towards better predicting where to optimise fertiliser application. Fertiliser is a costly intervention, and you want to make sure that it's a cost-effective intervention when you apply it, and these remotely sensed data could be very much used for that purpose. We've shown that structural and spectral changes in radiator pine canopies associated with needle depth can be quantified using imagery from both UAV and satellite. So on the left-hand side here, we're looking at imagery which shows very clearly needle depth from trees which were poisoned in a stand in group sizes of 1 ranging through 16. We got sick of waiting for the disease to turn up, so we poisoned them. And you can see it very clearly within this imagery. And if we look at one of these indexes in the middle here, NDVI, and you look at the progression through time since the poisoning, you can see a very clear decline in the NDVI for the green bars, which is basically a data collected from the UAV. But also you can see a decline in the orange bar, which is data collected from satellite. Why is this important? Well, because it points towards the fact that we can develop a system where we can use satellite data to monitor across broad areas and then combine other data sources such as those from a UAV to supplement this in hot spots where the disease is starting to break out. So it points towards the fact we can develop an overarching monitoring system for New Zealand. And I think that would be a really, really exciting development. I'd like to move on to the management side of things a bit. And we've done a lot of work over the Gcff program around optimisation of final crop stand density. You've probably heard me talk about it before. So as I've mentioned before, final stand density is an important determinant of crop volume and value. And empirical models included within Forecaster widely used to predict optimal stand density, final crop density at the stand level. They don't predict it spatially. So large-scale spatial surfaces of optimal stand density could be useful for forest managers. And so as a result, we've developed a very simple model that takes site index, 300 index, the value of all log grades, it's responsive to all log grades, the pruning cost and the rotation age. And we've used this to predict optimal stand density. This spatial prediction gives you a very similar result to Forecaster. It's basically the same, except it's spatial. So it's quite a useful method. And of course you make assumptions in generating maps. The assumption I've made here is that these are the average log values from 1995 through to 2017. But of course you can change these assumptions to suit your particular situation. But anyway, for the structural grade regimes, the model predicts mean stocking of 676 stems per hectare throughout New Zealand, which is quite a bit higher than the actual stocking of 500 stems per hectare, but actually coincides with a slide that John has produced around trial data showing that the optimum for this trial data does lie at 600 or above. So it's given us a bit of confidence around this. The key figure I want you to remember from my presentation is the figure of 1.7 billion. This is the amount of money that we could add to the plantation estate value if we grew at optimal stocking. And I want all of the forest growers in this room to share this value and think about what sort of stocking you're growing on your estate and how you could change this to actually optimise value within your estate. We also have a surface for prune regimes, and it shows a mean stocking of 356 stems per hectare. Sorry, I probably should have pointed out that this is structural grade regimes on the left and prune on the right, although that may be pretty obvious by now. And of course another output from this model is that you can predict value. So if you can get value from pruned and structural grade regimes, you can predict a relative value. And the colours on this chart show, the blue colours show where pruning is more profitable than structural grade regimes. The red colours show where structural grade regimes are more profitable than pruning. And so you can look at the changes through time. If we look at the first slide here, this is using average log prices over the entire period. You can see that pruning was actually more profitable throughout New Zealand. As we shift through time, you can see pruning sort of reached its peak around 2000 and 2004. And then you started seeing a change, and then 2010 to 2014, structural grade regimes became more profitable. The last few years, we've seen a resurgence in the profitability of structural grade regimes within the Central North Island. But you can easily see from these sort of outputs that you can quite quickly get a handle on your estate where it's most profitable to grow different regimes, which of course is a major decision point as well as the stocking for a number of growers. Thank you.
Thanks, Mike. Well, thanks very much for that, Mike. We're just going to move into another area where we're looking to improve our ability to monitor and manage what's going on in the forest. And we're just going to start looking at some of the biological interactions that go on. Now, within a forest, trees don't grow in isolation. They're affected by soil microbes that do things like keeping the resources available, produce phytohormones that go into the tree and affect the growth that is developed from those nutrients. And they also play a role in enhancing the tolerance of the tree once it has grown to various stresses, so therefore protect the value of what you've been able to grow. And within the Gcff program, we've been able to bring together a lot of resources and massively advance our ability to monitor what's going on, the activity of these beneficial microbes in response to a range of different treatments, a lot of conventional forest management practices to see how these beneficial systems, that engine of the soil and the microbes, how that ticks over and how that responds to the things we do in the forest. And going beyond just monitoring and seeing what happens, we've actually developed some treatments which we now can consistently use to enhance beneficial activity. So again, we're getting more out of these biological interactions rather than just observing them. So here we have an example from one of our long-term trials. So I've tried to keep it as simple as possible, but basically on the left here we have a relative measure of the ability of the soil microbes to fix nitrogen, basically pull nitrogen out of the air and turn it into available forms for plants within the soil. And what we found is that the use of fertiliser decreased this ability markedly, and it wasn't a short-term reduction in the microbial community to do this. It was actually a very long-term effect. We were seeing it 17 years after fertiliser events stopped. It wasn't excessive fertiliser use, but the fact that that effect persisted so long after fertiliser ceased gave us a bit of pause for thought around the swings and roundabouts where you think you're getting a short-term benefit but for potentially a long-term detriment from basically losing that biological function. However, on the flip side, we did see some really positive effects coming from that fertiliser use as well. So again, 17 years after the fertiliser stopped, at the same site, we saw that the plots that had had that fertiliser treatment, the soil microbes had a greater capacity to enhance the stress tolerance of those trees. So again, there's a lot of science that goes in very long words around what we're looking for and how we're doing this work with the microbes. But the simple story is that these microbes that produce enzymes that help the trees make more stress tolerant, they were far more active after they'd been exposed to fertiliser. So we were really interested in that last one, and we tried to use this information to see if we could actually manage the microbes. Could we set up directed experiments to make the microbes enhance plant stress tolerance? So we did some work with a number of clones, and we found that, yep, we could use nitrogen fertiliser to increase this biological activity. And we saw positive results that extended for at least 18 months after we added the fertiliser. And then when we tested those seedlings with drought, we found positive results that basically the internal signals saying how stressed they were decreased. They were more stress tolerant because of something we'd done to the soil to affect the microbes that had a feedback effect on the plants. We also have ongoing work around biuret, so I talked about that briefly in the nursery talk, but this is basically, it's a molecule, it's a byproduct of urea production, and I first got interested in it because it's capable of stimulating microbial activity. It is toxic to plants. My first bit of work was trying to find a sweet spot where it was doing good things for the microbes, but it wasn't doing bad things to the trees. But then we found out that Pinus radiata is completely immune to it. You can add as much as you want and it just says yay and is happy. So that opened the door basically. That meant we could do a lot more than we thought we originally could. So we've used it in the nursery trials as discussed, but we're also applying it in forests as well. And we're linking it with new balm so we can understand the best possible timing to be adding it into our forest systems. And because of that toxic effect, we also looked at the opportunities to use it as a weed control agent while also benefiting the trees as well. And overall, our results have been consistently positive. We're getting consistent gains in growth from adding biuret at very low rates compared to conventional nitrogen fertilisers, and the weed control effects are also looking promising as well. So here's just an example of some of the productivity gains we're having. So at one of our accelerator trials, which I'll give a little bit more information on later, we added 2 very small doses at total 12.5 kilograms of nitrogen per hectare, and we're seeing significant gains in height, but also the canopy area of the trees as well. And again, this was quite quick after we added our treatments. In terms of weed control, here's an example of some of the work we've been doing. So we had a number of weed species. We put them in soil that we treated with variable levels of biuret. We let those seeds germinate to see what would happen. We didn't see a particular suppression of germination, but what we did see is that the more biuret you had, the quicker those weeds would then die. And in fact, at the medium and high rates, we were starting to see those weeds dying before they could reproduce. So what you can see in the background here is the trees that germinated in the first cohort, and the green sort of mat, that's their progeny. But at the higher rates, the medium and particularly the high rate of biuret, they were all basically dying before they could produce any seed. So we're quite enthusiastic about this response. But we're also looking at using conventional nutrients as well, but in much more efficient ways. And this comes to that monitoring and management. If we can understand the site, understand the trees, we can get a window into exactly what combination of nutrients are needed rather than the standard, well, let's throw on 200 kilograms of nitrogen as urea and see what happens. So we're looking at a balanced nutrition approach where we're combining nitrogen and phosphorus and other elements to try and get the optimal balance of nutrients within a site to support tree growth. And another avenue that's being explored is the application of foliar fertilisers, basically getting nutrients directly into the tree and bypassing the soil and avoiding some of the environmental issues that would go with bulk application of nutrients. Now, some trials have been going underway, have been exploring this for a number of years, and we're seeing positive results, certainly from the balanced nutrient application, and we're also seeing good initial results from the foliar fertilisers, which we're actually able to add through UAVs because the quantities are so small. And again, that opens the door to much greater precision as well. And linked with this, there have been environmental studies that have shown that these reductions in precision nutrient management is also related to reduced environmental impacts as well. And speaking of that, we've got a short video now talking about the work that we're doing to understand the effect of forest management and nutrient management on water quality in forests.
Well, there's been a long history of fertiliser research in New Zealand and other countries around the world with conifer crops, and so on infertile soils you can actually double the growth rate. The industry is working with Scion to do these lysimeter studies where the profile has been sampled over time, and through that we'll be able to understand the movement of nutrients, the cycling of nutrients and the availability of nutrients.
Okay, if we add nitrogen fertilizer, is it going to leach? How quickly will it leach? At what rate does it start to leach? And those are some of the questions that we can answer using this setup. Okay, this is one of our lysimeter holes. So what we've done here is we've dug horizontally into the soil and installed two types of lysimeters. We've got leachate collectors, which is what's attached to these hoses here. All the leachate gets collected in these containers. And then we have resin lysimeters, which look like this. So these are installed in there. As the water percolates through the soil, it percolates through our lysimeter. The resin in the middle of the lysimeter captures all of the mineral nitrogen, and we can come back 6 months later, 1 month later, measure how much nitrogen is in that resin, and that tells us how much has come through the soil in that period of time.
Right. So I'm going to present on how to protect forest value. So back to this wheel diagram here. The Gcff program, we've also had a focus on how to protect forest value. We have extended our capability to maximise end rotation stand value and to support sustainable practice during harvest. Steepland harvesting is one of the highest risks to our licence to operate. Although planted forests protect land from erosion for the majority of the rotation, clear-cut harvesting does result in a risk of erosion on steepland. In the Gcff program, we have had a research area focused on reducing the window of vulnerability. The window of vulnerability describes the elevated risk of landslides after a forest has been harvested and before the next crop has reached canopy closure and root site occupancy. This window is about 5 to 6 years. Our key achievements in this project area are an Erode NZ mobile application and National Erosion Debris Flow Database prototypes to capture what is happening out there. A tree species root strength library, a new field trial to close that window of vulnerability using radiata and willow pole mixtures. And we've also used LiDAR to map erosion scars and the impact on productivity. This particular work we've done has allowed us to develop a new program on the economics of steepland harvesting options. So it's allowed us to branch out and do more work, which has been really good. Sustainable nutrient management at harvest is also a high priority in New Zealand's forests, particularly as about a third of our radiata pine forests are already planted on low nutrient soils. Our planted forests can have a range in nutrients which is held in the soil, forest floor and live tree biomass. This figure that you see here with the 6 sites shows nitrogen in the mineral soil, the forest floor, stem wood, stem bark, and slash left on site after harvest. What you will notice is that some sites have more nitrogen in mineral soil compared to others. That's the brown box there. And the amount of nitrogen that is plant available, which is shown in the yellow box, is only a very small percent of this total nitrogen in the mineral soil. What you'll also notice is that the forest floor is a significant proportion of on-site at Woodhill, while at Berwick, the forest floor is a much smaller proportion of the whole ecosystem nitrogen. Therefore, how Woodhill is harvested in terms of its residues will have a high importance on the supply of nutrients to the next rotation and multiple rotations out. The data that has supported this figure has come from a long-term sustainable productivity trial series, which was installed to look at the impact of harvest residue removal and fertiliser amendment on long-term site nutrients and productivity. We were fortunate to get end rotation data out of some of these sites, and what we found was that forest floor holds a high proportion of the forest ecosystem nutrients and important to retain on site at harvest. For example, forest floor at the end of rotation can hold between 200 to 500 kilograms of nitrogen per hectare and between 15 to 20 kilograms of phosphorus per hectare. Also, the removal of harvest residue impacts sites with low nutrient capital the most. The nutrient balance model can be used to answer if nutrient supply is sustainable over multiple rotations and what it means for productivity. So you don't have to go out there and measure those ecosystem pools. You use this model. This is demonstrated in the figure here, which shows an output from the nutrient balance model for nitrogen and the biomass in the forest floor on the y-axis there over multiple rotations. The nutrient pool and productivity data we have collected from that long-term sustainable productivity trial series has enabled us to test this model to investigate if organic matter removal harvesting options for a given site are sustainable. This brings me to the value of long-term trials. This diagram here shows a few of the trials that Scion has on a timeline. The black horizontal line represents this year, 2018. What you will notice is that there are a number of trials that have passed the end of their rotation and gone, or very nearly at the end. The graph at the bottom there shows the number of registered trials at Scion. The peak time that you can see in that graph is from 1980 through to 1990, where we had over 1,000 trials registered in that 10-year period. Looking into the future, we're here now at the end of rotation of that peak installation time. We have been lucky enough to capture a number of those long-term trials through the Growing Confidence in Forestry's Future program at the end of their rotation. The first is the long-term sustainable productivity trial series, and the second is the silvicultural breeds trial. I'll summarise those two trials in the next couple of slides. Also, we have new trials that have gone in under this program that are the start of our next legacy. So the long-term sustainable productivity trial series was installed 3 decades ago to look at the impact of harvest residue removal on long-term nutrient supply and productivity, and if the addition of fertiliser could amend that. These trials are part of a global network investigating the removal of harvest residues. We were lucky enough to get data out of 3 of these sites, Woodhill, Tarawera and Berwick. The remaining 3 were lost. Kinleith and Burnham were lost to dairy farms, and Golden Downs was severely impacted by wind. The trial series has been highly important as it has offered over-rotation and end-rotation nutrient pool and growth data to validate that new bar model, so you don't need to go out and measure everything, and the impact of these treatments on wood quality. The second long-term trial in which we have collected end-of-rotation data is a silvicultural breeds trial. These trials have added significant value in quantifying the effect of stand density, seed lot, site on yield, total value, relative value and wood properties. They have also allowed us to confirm results from the optimal final crop stocking study and enabled us to realise genetic gain information to be updated with older stands. So to end this section, on protecting forest value, the growing confidence in Forestry's future program has extended our capability to maximise stand value, particularly through the use of long-term trials, and support sustainable practice during harvest.
Thanks very much, Loretta. Now we're moving on to the last section, which is a bit of a summary, but it also talks about how we're trying to put together all of the research that we've generated under the GCFF into one package, which is the Accelerated Trial Series, which Loretta alluded to as being sort of the next flagship, the big legacy that we're leaving. And again, a huge team of people involved in establishing these large installations, simply because it takes a lot to get them in the ground, but also the fact that there's a lot of stuff that we're monitoring, all the things that we've heard about, we're involved, we're applying to these sites to understand them as best we can so we can treat them as best we can. So, as I said, it basically pulls together everything we've talked about in these 6 sites, which we've been able to establish with fantastic support from a number of companies, and also with a lot of guidance and support as well from the TST group, who have been involved in making the decisions around what are the right type of sites we should be looking at, what is the kind of value we're looking to deliver from the end of the GCFF, but also from the future research outcomes that these sites are going to be providing. So, if you consider this graph, a site has a potential productivity which we'll say is determined by its thermodynamic limit, basically the amount of light it gets. And if you consider our business as usual, we're not really approaching that. But what we're looking at is, within the Accelerated Trial Series, to take our knowledge around matching genetics to site, to the work we've done around stimulating soil microbes to improve various functions that support productivity, to improve the precision and timing and fertiliser use, to get to that level. But in the however many years it's going to take us to get to that point, we're fairly well aware that climate change is going to come along. So what was our target is no longer our target. It might be higher and it might be lower. So therefore, what things might we need to do to enhance the tolerance of the trees to deal with the climate change so they can still maximise their productivity at this particular site? Now, this highly integrated approach, where we're pulling together all of the areas of science that we've been applying under the GCFF, is already producing some positive results. Now, I'm not going to go too much into the details of this one because it sort of combines phenotyping, soil work, nutritional work, and microbiological research to sort of improve our understanding of how different genotypes respond to stress, how they work with microbes, and how they respond to treatments. But the take-home message from this is that by putting all of the science together, we understand that some of the genotypes that we're looking to plant out, if there's, say, a drought stress or a nutrient stress, we now have new treatments that will encourage microbes to help them get over that stress. But on the other hand, we also have some other genotypes, these fellows on the end, they're naturally really good at defeating those stresses, at dealing with them themselves. But if you try and stimulate the microbes, you actually go in the other direction. So we're starting to realise that there are some genotypes we can do all kinds of things to make them better, but other genotypes it's just simply better for us to leave them alone. They'll probably manage by themselves. And that's a level of precision we didn't think we'd be able to get to. Other things we're deploying at these sites include our ability to monitor them, the data we can collect. So for example, at this site, overflights with UAV have allowed us to build up tree health inventories, vegetation indices, so we can see the weeds that are coming through with them. And we're also identifying cultivation effects as well, where we've done afforestation work. And we can use tools like electromagnetic sensors, which provide us with detailed maps of the soil and soil properties over a very wide area quite rapidly. And again, we can link that back to tree performance, and we can use this information to inform the treatments that we're going to be applying, not block by block, but potentially area by area within the site, based on our understanding of those soil properties. So the take-home message out of this is the greater level of knowledge that we can get from these sites, and indeed almost any forest now, is just going to enable greater precision in our management. So coming to the legacy of what the GCFF program is going to sort of provide, coming back to the diagram that we put up in the front, where we targeted improved yields, better opportunities for mid-rotation, improved opportunities for disease resistance and the phenotyping platform. I think we really have hit all of those targets in some way. We're making huge advances in our ability to monitor all aspects of the forest. We've got a new understanding of biological interactions that support forest productivity now and for future rotations. And we also have better options for more precise and sustainable management of the forests. And some of the work that John alluded to, where we have new systems to quantify wood quality and value as well. And finally, the accelerated trials and some of the other trials that we've produced, they're going to be providing value well beyond the lifespan of this program and indeed the subsequent program that will follow it. So I hope that we've left ourselves in a position where we've added a lot of value, but we're also going to be continuing to add value for many years to come. And at the end, we'd also like to give a huge thanks to Peter Clinton for leading this project, but also to Annette Brockerhoff for her sterling efforts to manage us all and to get us all delivering things on time. And again, it was mentioned at the start, but the industry TST team that's been involved in this project through the years has been invaluable. The support they've provided, discussions, new ideas, and also supporting access to sites. It wouldn't have been possible without them. So thank you very much for your attention.